optimization problems with about 4 to 8 billion variables. If you set it up in the right way, you can solve it fairly efficiently on the laptop. Here's another trick that's quite useful, randomization. So those of you who've taken something like randomized algorithms class or the probabilistic method by Alon, Spencer, and others, that's like the sort of warm-up exercise. But that already is extremely useful in its own right. Let's say I want to find the maximum, right? And I have a really large set, but I don't necessarily need to find the absolute maximum, I just want to find something that's really good. Then what I can do is I can go and just pick the approximate maximum by picking a random set of terms. Let's say we pick n terms. And then I take the maximum of this subset, and so it turns out that this is a very easy to remember rule. If I randomly select 59 instances, then with 95% probability I'm at least in the 95% quantile. It's a very easy to remember rule. And this can make your life a lot easier. Basically, it can turn algorithms that otherwise are linear time into constant. Now, let's just derive this thing, because it's so easy. So, we just look at the cumulative distribution function. And, well, the probability that the CDF is less than epsilon. Just 1 minus epsilon to the n. That's delta. So we go and solve for n. We get this nice expression here, which actually is less equal than log delta over epsilon. And I plug things in here, so basically I get the 5% and the 95%, and done. So it's a very, very straightforward reasoning.
The inside, outside F or inside?
Pardon?
The F on maximum outside.
Okay, so that is inside, and then it turns out, as we saw, that the maximum of a bunch of random variables has as its CDF the product of the CDFs.
Yes.
That's what I'm exploiting. That's the CDF. And then you just solve for it. It's very straightforward. And, randomization is of course a lot more general, so you can use it to find a good solution, you can find good majority, and there's a lot more work. So, these are great rules. I'm going to conclude with, given that it's Valentine's Day, with a bit of sweets and cake. So, submodular maximization. So, the idea there is, well, maybe you want to make your girlfriend or your boyfriend happy, and so you want to bring them, let's say, some sweets. Maybe she really likes chocolates. Now, I don't know how much she likes chocolates, but maybe after the 4th or 5th piece of chocolate, she's probably a bit sick of it, and she would rather maybe have something, healthier, like an apple or some cake or whatever. Not necessarily it's very healthy, but anyway, maybe she gets bored. Okay, so now, if you can but you know that this is maybe an order of preference. So, who would pick only those four chocolates? Well, probably nobody would. You would probably go and mix and match things a little bit. Well, why? Because essentially, if I already have eaten, let's say, 2 chocolate bars, and the 3rd chocolate bar is going to make me less happy than maybe an apple will, even if I like chocolates a lot more than apple. And this is an instance of what's called submodularity. So that says that the improvement, so there's a monotonically increasing function on sets, that the improvement that I'm getting by adding a set C to A is greater than the improvement that I'm getting by adding the set C to B if A is a subset of B. In other words, if I give a poor person a tax break of $100, it makes a big difference to them. If I give a billionaire a tax break of $100, it doesn't make such a big difference. You can draw two conclusions from it. Either you should give the poor people tax breaks, or you should give the millionaires more. But basically, otherwise, it's not going to make you happy. So it's this diminishing returns property that occurs a lot in both machine learning and also in human behavior. And this fortunately has an extremely simple algorithm to maximize it. You just greedily add things. So in the case of the chocolates, you would call your girlfriend and ask her, well, what do you like? Well, okay, I like chocolate. Good, okay, chocolate's in the box. What else do you like now that you already have chocolate? Well, apple. And you keep on adding them. And you can prove that even though the entire optimization problem may be NP hard, it typically is, you can actually solve, at least with a good approximation guarantee, namely 1 minus 1 over e, the problem by a simple greedy procedure. And this has proven extremely popular. So Andreas Krause and Carlos Gestrin have written a whole lot of really cool papers on that idea. And so if you'd like to know more about this, you should go to submodularity.org and you'll see a lot of those instances. So for instance, also last week's Best Paper Prize winner at Wisdom used that type of techniques for deciding basically which rewards to give to whom in marketing on networks. Again, it's a diminishing returns property. In other words, if I've already spammed you about living social, then if another person spams you about living social, well, the chances that you click on the second ad are a lot less than whether you clicked on mine. Okay, so you can use it for a lot of things: feature selection, active learning. You can monitor and try to actively monitor the disease spread networks. You can summarize documents with it. You can learn graphical models. You can extend it. So Dan Golovin and Andreas Krause have done interesting things in the context of decision trees there. So it's a very powerful tool. Okay, so I think we're... Yes?
When you keep adding subset of x,
at some point you're out of capacity.
Lines heuristics, or is there something more to that, or it's not really?
Okay, so basically this is maximization under a capacity constraint. Let's say, for instance, I'm a doctor and I want to find out why you're sick, but my entire budget is maybe $100. Then, in which way should I go about, subjecting you to various medical tests to find out what your disease is? And so it turns out that this is a generalization of the submodular optimization problem. This is exactly what Golovin and Krause studied. And you can show that if you try to forward predict your greedy expected return, you're going to actually do well in terms of finding a solution that's near optimal. So there are a lot of weighted versions and so on of this procedure that you can use. Or for instance, there are submodular secretary problems. And I think it also has another name than the secretary problem. Who knows what the secretary problem is? Okay. So the secretary problem is basically you want to hire a secretary. And you're going to see maybe 1,000 secretaries. And at each time you look at her, you decide, is she good enough? And at that point you need to commit and decide, well, whether you want to hire her as a secretary or not. I mean, it's also called a marriage problem without divorce, right? And, then the regret that you're going to have is, the difference between the secretary that you hired and the best secretary that there would have been within that pool. And a good strategy is basically you ignore the first one over E and basically find out what the best one is among them, and the next one that's higher than that threshold, you hire her. Now, there's a submodular secretary problem. It's basically, suppose you want to build a team for some purpose, maybe for engineering team or whatever, and each engineer contributes something to the overall task, and they all need to complement each other. Or you want to build a soccer team, and you can't have more than one goalkeeper. That's not very useful. So basically a sequence of players come along, and you need to decide at any time who to pick, and you have a maximum team size. And again, that same greedy procedure will work. What you do is you basically run the secretary algorithm on the first part, then you run it on the increment, and you keep on going. And you can prove that this is also then not a stupid thing to do, but you can't prove very tight bounds for that. Any other questions on that? I think we're out of time. It's exactly 7 o'clock. So we've done a lot of optimization today. A bit more to read up if you want to. And there'll be also the optimizations chapter from the Learning with Kernels book that you can download. Okay. So the assignment should be out by tomorrow sometime.